Okay, folks, thanks for joining. Little soft rock favorites there by Lionel Richie. In litho world, we like the 80s because things were so much simpler back then. Not so now. What I'm going to talk about today is a pretty advanced topic. It's actually the most advanced topic in semiconductors today. It's called EUV lithography. On this, I'm going to do a hardware deep dive on the tools and systems that go into this. First, because it is an advanced topic, I'm going to just get a little bit of house cleaning out of the way for the general audience, um, so that they understand what this is, because again, it's a very advanced topic. Okay, silicon wafers and how they're made and how microchips are made. So they're made upon these silicon wafers. They're pure crystalline silicon. Um, you'll see a grid here of microchips that are imaged on this, are created upon this surface. And at the end of the day, when it's all done in processing, they'll dice it out and put it in a package, and then that goes onto a board, like it goes in your cell phone. So how are they made? They're made by stacking a bunch of layers upon this substrate. So here, this is a cross-sectional image, a SEM image, image with an electron beam. If you were to slice through this and look at all the different layers that are stacked up, you start with the transistor made in silicon, and then most of them are metal interconnects. So you can see here, you can barely see it, metal one, and then it gets larger in geometry size. But basically, how this process works, you deposit a layer like metal or dielectric that you're going to make the circuit with. You then coat organic film that's photosensitive called photoresist. You optically image the pattern on that. You develop it just like a photograph. Although this photograph is very tiny features on the nanometer scale. And then once it's developed, you send it out to like etch a pattern into it, and then you remove the film, and then you keep repeating this process. Modern chips have like 100 layers in them to create like a modern, like your iPhone chip. Okay, so that's what semiconductor patterning is. It's the process of stacking up all these patterns on top of each other to create a semiconductor device. But in the world of semiconductor patterning, there's a lot of different topics, and each one of these little topics I kind of outline here, you can make like a whole career out of. So at the heart of this process is here this the lithography process, which is making that organic film, the image of the circuit. But there's a bunch of other topics that are related, like for example, photoresist is the photofilm, and developers is developer chemicals. There's process technologies like etch, right, that use to transfer the pattern. But the heart again is this lithography process here. So there's other lithography. I just put a bucket of other lithography, such as electron beam lithography is used to make the masks or the master patterns. The heart of this process, though, or the workhorse to make microchips, is called projection lithography. And there's various generations of that, and that's where EUV comes in. So EUVs and the projection lithography plays well to mass production. So you can print very small circuit parts on a mass scale. There's different generations. The current generation, the latest and greatest, is called EUV low NA. There's another generation called that will be coming in a couple of years called high NA. But today I'm going to just talk about the current generation and the hardware that goes into it. Okay, what is projection lithography? Projection lithography, simple form, you take photons, light, you shine them through a master circuit pattern. They go through a lens that reduces the pattern down to a chip level. It's actually 4x reduction. And then it steps and repeats that all over the wafer, and you make a grid of chips. So the whole goal here is, with each of these generations of lithography, is to print smaller and smaller features. So there's an optical equation called the Rayleigh criterion that describes the minimum resolvable geometry for an optical system. And this is an old equation. It goes back to the 1800s, but it's used to describe any system with a lens, a microscope, a telescope, the camera in your iPhone. So how this works is CD is critical dimension, so that's the resolution or the minimum geometry. equals the K1 scaling factor. This is a measure of how blurry, so it's like a scalar. You don't really need to worry about this now. Just measure how blurry the image is times the wavelength of light. So you can see right off the bat, if you're reducing the wavelength of light that you're using coming through here with, you can make a smaller geometry, right? And then that's divided by the numerical aperture. So this is how big this lens is here. The bigger the lens, the smaller the geometry. So we're in the 6th generation of projection lithography. We're in EUV here, but the prior 5 had successive reduction in the wavelength, kind of small jumps, but they were very important. And then we get to EUV, which was like a 10x improvement, right? So big change there right off the bat. But the lens size got much smaller. Despite that, the resolution improved significantly. So I'm going to talk about this today, low NA EUV, 5th generation projection lithography, state of the art. Okay, so what's different with EUV? That prior diagram I showed you is how all prior generations of projection litho worked. Simple. It's all, light goes through, comes down to the wafer. But EUV is much different. Here's a diagram of an EUV scanner. You can see right off the bat, it's a lot more complex. So first of all, the source light used excimer laser as the prior generation. EUV uses a tin plasma. Now there is an excimer laser involved, but the tin plasma itself is what generates the UV light. The lens is completely transparent for the prior gen. It's a reflective optical system for EUV. Third, the ambient pressure, or I'm sorry, the light path is just uses ambient pressure. So it's the same as the factory floor, no different. But however, EUV, you really can't have anything in the light path for EUV. So it's the entire light path here and the entire tool itself is under vacuum. Now this leads to a couple other downstream changes. So the wafer chuck, like where the wafer sits here, that in the prior gen they pulled a small vacuum under it to hold it in place while it moved around. Obviously you can't have a vacuum chuck work in a vacuum, so they use an electrostatic chuck for EUV. This is important for a number of reasons. It actually very important for pattern placement. Not going to talk about it today, but maybe I'll do another live stream on that. And then the reticle. The reticle is fully transparent with the prior gen, and it has what's called an enclosed pellicle. What is a pellicle? A pellicle is a film that's kind of suspended over the circuit pattern here. It's transparent, and it keeps any particles that might fall on the mask here, the master pattern, from being in focus. So it keeps them out of focus so that they don't get repeated over and over again and kill every chip that you have, right? Because then you would be imaging a defect onto the chip. With EUV, it's a reflective mask, first of all, but the pellicle situation is much more complex for EUV. The jury's out about like exactly how many companies are using a pellicle. I'm not gonna go into the details of pellicle today. I may be participating in an article on that in the coming weeks, so there'll be a deep dive on that coming soon. But even if you had a pellicle, it can't be enclosed because you're going in and out of a vacuum. This, outside the tool's ambient, and so once you go in the tool, it would explode, right? If it was actually fully enclosed, and if it, the pellicle was under vacuum, it went out, it would implode, right? So it's not 100%. Even if you have a pellicle, it's not 100% protection from particles getting on the master pattern. So these are the 5 big hardware changes that are present now with EUV. Okay, yeah, just to explain a little bit about how a lithography cluster works. So a lithography cluster is a track and the scanner, this is the projection lithography optics. So wafers are coming into the tool this way here. This is the track, and here's the dividing line. This is the scanner over here where this guy is. So the wafers come into, so the track is basically the chemical processing piece of this. Wafers come in, they get coated with that organic film, they get baked, then they get sent into the scanner. It's imaged optically, and then it gets sent back in to the track. It's baked again, and it's developed with like a wet chemistry, much like a photograph developer. And then it comes out and it goes, over to etch or something that's gonna, transfer into something real like metal. Um, Now the cluster itself, it's it's never really done in a fab clustering tools like this because of the logistics of it. If one tool goes down, then the other tools are just going to sit idle because it can't run. Time is money on these tools, very expensive tools. Um, the lithography cluster is the only two tools in the fab that are clustered. The reason is the chemistry is very sensitive to like time delays and contamination and things like that. So it's always been a clustered system. Early on, it was very sensitive. The early resists were very sensitive to the environment and timing delays. The later generations got a lot more robust, but EUV now is again sensitive, especially the metal oxide resists that are used specifically for EUV are sensitive to time delays and the environment. So it'll always be a clustered system here. Now this came from IMEC, and it was an article about EUV, but I noticed actually this wasn't an EUV scanner over here. I believe it's an immersion scanner. How do I know it's not an EUV scanner? There's no crane. So EUV scanners are the only tool in a fab that has its own crane. That's the crane's needed to perform the maintenance, lifts part of the tool up. People can get inside there, maintain the tool. So I could tell right off the bat, there's no crane here. It's not an EUV tool. It's probably an immersion tool. So let's look at an EUV tool. Here's a picture of an EUV tool. It's a big box, right? Tracks over here. I believe this is Albany Nanotech, but here's the crane. You can see there's a crane. Each crane serves two tools. So you kind of maximize the use of that crane. It'll go between, if there was another tool, I think it'd be over here. What do you notice here? It's a big box. That's the way most semiconductor tools are. They've got paneling all over the components. It's blocked off from the outside, even the factory environment. So not very interesting. Wafers go in, magic happens, and then they come out and they have these tiny circuit patterns on it. So let's start stripping down the tool. Here's the same tool, but it's got the paneling off on the source of the tool. This is where the tin plasma. This is the source piece down here in this corner. Early days of EUV, this was a common scene in the fab. You wouldn't see the paneling on the source. There'd usually be 2 or 3 guys there huddled around the thing trying to keep it running. The engineering challenges of EUV source are enormous. In the early days, it wasn't very reliable. Today, it is reliable, so it's normally enclosed now and doesn't require nearly as much attention. But that was a common scene early on. All right, let's just talk about the entire. So I was talking here about the source and the scanner. That's only part of it. Underneath this and on the floor below will be all this is a CO2 drive laser that's used to make the tin plasma. This is underneath. You don't want to waste valuable factory floor space having all this equipment so that you have like a bunch of other support equipment, power amplifiers, of course the laser itself, very powerful CO2 laser. It can cut metal. And indeed it's creating a metal plasma. This is a little diagram. I'll show you the source in a minute. Remember this number, 50 kilohertz, the droplets, the tin droplets. 50 kilohertz. How fast is 50 kilohertz? It's 50,000 times a second. Pretty fast. Okay, yeah, another. So this is like, yeah, so the CO2 drive laser would be underneath in the floor below the scanner. You don't want to waste valuable clean room space having all these components if they're not needed. So then it's piped up into the source. So that laser beam comes in here. There's droplets of tin passing in front of it. It hits it and strikes a plasma. It's collected by this mirror and then sent into the scanner. There's a big collector mirror here. All right, let's strip down the tool and look inside. I think, okay, what I'll do, I'll show you the path a couple things take through this tool. So I'll show you how the wafers move through the tool. Then I'll talk about how the reticle moves through the tool, and which is the master pattern, and how a photon moves through. So the track would be over here, and the wafers would be coming in here. This robot here would then grab it. It would put it on a pre-aligner that aligns a notch, and then ultimately it gets passed down to the first stage here, the wafer stage. So there's 2 stages, 1 and 2. The first stage would do all the alignment metrology, so find the position of the prior pattern so it knows where to place the pattern. And then once it's done that metrology, it passes it over to the exposure side, and then the exposure happens. It images the pattern over in a grid over and over again. It then comes back over here, gets passed back to the robot, and goes back into the track. Okay, how does the reticle comes in? I believe it comes in through the top. If it's automated, you can also load it from the front of the tool. If you're manually loading a reticle, it ultimately comes in, goes to a stocker, and it'll end up here on the reticle stage. So this is where the master pattern would sit. Everything goes through a vacuum load lock when it goes in and out of the tool, including the wafers. And then a photon. So the source is here, actually goes like below the floor. It directs the incoming beam at an upward angle into the first illuminator mirror. There's 4 mirrors on the illumination side. It hits the reticle. Then there's 6 mirrors on the projection lens side, and then it hits the wafer on this stage here. I believe the EUV, the high NA, the next system will have the light path enter like on the upper top of the tool at a horizontal angle. Okay, the stages. So the stages are really interesting. They float on like this back plane, or it's just a planar surface. So they're actually suspended by with air pucks. There's 2 stages. So the air puck, it's like pushing out at like a higher pressure and sucking in right around it, around the puck at a slightly lower rate. So that actually will suspend it, and it'll float on like in a frictionless form. These stages are able to control position down to the single nanometer scale, like X and Y, right? And there's 6 axes: X, Y, Z, which is like up, down. There's tilt, tilt X, tilt Y, and rotation. So 6 different ways to control the movement of the stage. Again, it's like nanometer scale accuracy. The reason there's 2 stages is to maximize the amount of metrology. So maximizing the metrology is absolutely paramount for placing the pattern accurately. So what happens is one, and it has to do with also the productivity of the tool. So you don't want to waste any time inside this tool. Time is money on this tool. So while one wafer is getting all this, positional metrology, the other wafer is exposing, then they swap positions. So both sides are always operating 24 hours a day, 7 days a week. There's no one guy sitting, one side sitting idle while something else is happening. Again, so arguably these are like the one of the most expensive tool, actually probably the second most expensive tool component behind the lens. So the importance of this, maximizing alignment metrology justified the investment in 2 stages, not 1 stage. Okay, cool. I have a cool little GIF here, or a GIF. It's not peanut butter. I've always called it GIF. But this is just to show you like the speed at which the tool operates. These stages are operating independently. Again, they're floating on a frictionless surface. It doesn't show the swap here. I wish it did. You wouldn't see purple light. You can't see EUV light, of course. You can't see light in that range. It's also a vacuum. You can see the reticle moving around. You see that big robot on the left there. So that's actually a powerful robot. It actually can lift like heavy objects up. You could use it like in an automotive factory, drop an engine in a car. But the reason they use it in scanners is because it can place a wafer. It can move around like in different components, very all over the place. So it's configurable, but it's also has very good placement accuracy. So a wafer is only like a couple ounces. So it's a little bit overkill, right? It can lift heavy object, but they use it, and it's also relatively cheap compared to the other components. All right, so here's a diagram from Cymer at the time. Cymer was acquired by ASML, but Cymer makes the sources. They make lasers too, but they make this EUV source. A couple components. You have a droplet generator. It's streaming droplets into in front of the laser. The laser's coming in here. CO2 drive laser hits a droplet here. That generates EUV light, bounces off this collector mirror, and then gets focused inside into the scanner. A couple components, like obviously you need to calibrate that stream, so there's something that catches the droplets here. You need to target the droplets. They're very small, so you get like a targeting camera. You get sensors that sense the light. So there's quite a bit. It's a very complex source system. Okay, striking a tip plasma. So remember that number, 50,000 times a second. One of these droplets is turned into a plasma, vaporized. So you got this stream. It's on the microsecond scale. What you might not know is that there's a pre-pulse. So it comes in. It's a 30 micron droplet. They hit it with a weak pulse here, pre-pulse, and that flattens it into a pancake. So then it's like 50 microns in size. It's flattened out, and then they blast it with a much more powerful pulse. And that's what creates the plasma. That then gets reflected off the collector mirror and into the tool. So really 100,000 times a second are the pulses. So one, 2 pulses for each. Oops. Okay, so that collector mirror. Here's an image of that collector mirror. It's a pretty big mirror, almost a meter in size. Here's an image. It's made by Zeiss in Germany. Pretty impressive mirror. Let's talk more about that. So it's takes the brunt of this this plasma energy. So it's getting beat up pretty bad, and it actually has to get swapped out on a routine basis. So the lifetime, I'll talk about this. The mirror itself has like multiple layers. There's 80 layers, and then they put a cap on it to try to protect it. This cap from the energy can blister. You also can get like tin contamination because you're vaporizing tin. So that beats the mirror up over time. And what happens is, this is a plot of the reflectivity off the mirror over time. You can see it drop as you go out. These are in gigapulse scale, but that the reflectivity goes down. And at some point, you hit a level where you go. It's slowed the tool down to a point where we have to invest in a new mirror, and you do the maintenance, you swap the mirror, and then you're going down again. Arguably, this is a routine maintenance procedure. It's one of the most complex maintenance procedures in the fab, if not the most. You're swapping out a lens component, got to get calibrated after. In the early days, this is a long procedure, it's like a day. Then they got it down to a shift. But ASML now has it down to, I think, a few hours. They can perform this procedure. It's also the lifetime has been drastically improved. So now this is actually a very reliable thing. But again, it is a routine maintenance procedure that you have to do on one of these machines. Okay, how do the EUV mirrors work? So again, it's a multi-layer. So there's 80 layers of molybdenum and silicon. And why do they stack these multiple layers? So as EUV light comes in, only 2% gets reflected off each of these surfaces. So there's 40. There'll end up be 40 surfaces that get that reflect the light. When you add all this up, it's about 70% reflectance. Not a whole lot, really, right? It's not super efficient. So just remember that. We'll talk about that in a minute. Now, the reticle, the master pattern, has the exact same setup. It's 40 layers. But to make the pattern, it just puts an absorber is imaged with an electron beam in some areas. So this is 70% reflectance, right? And this ends up being 2. So it's not exactly black and white, which is unlike the prior gen stuff. Another thing is, what if you had a defect? Now it's almost impossible to coat 80 layers and not have some small particle somewhere in one of the films. So what do you do, right? Because that's going to be a defect that gets printed over and over again. First of all, just to see where they are, you need an EUV source. So that'll look down into this film, come back, hit a detector. Okay, I know where the defects are in my mask blank, but I can't use it because I got defects on it. So what do? They move the pattern around. They have a database of all their blanks and where all the defects are. And then a new design comes in the mask house, and they go, oh, can I use the absorber with this design to cover it up? So they'll move the absorber. Also, there's what's called non-functional pieces of the device, what's called fill. So they have a map of where they can block the defect in some way or put it in an area where it doesn't matter, and then that's how they get around this problem. They're probably down to like single digits now, but even like 1 if it was in the main reflective area would be is not allowed really. Okay, the optics. So we talked about the collector down here. So on the illumination side, there's 4 mirrors. Um, and then there's the reticle, which is also a mirror. And then there's 6 mirrors on the projection optics, which reduce the pattern down 4 times, and you pattern your chip. So, but there's 2 mirrors that are very unique on the illumination side. This what they call the facet mirrors. So what are they? These aren't a single mirror. These are an array of mirrors that you can control like where they're pointing at. And the reason they do this is that you might think it's just like a circle of light coming through. It's not. You want to create a pupil, like an image, and this has to do with what's called off-axis illumination. But in not going into all the details, but like for example, there's certain pupils that print certain geometries better. So what they do is they limit the number of geometries like a designer can use, and then they pick one of these pupils that prints the allowed geometries the best, and they're able to get better patterning performance out of it. But that's why you have these sort of movable mirror arrays are used to create these pupils. So this is absolutely so. This is called source mask optimization. So this is the source, the source pupil. You can dive in. You can make a whole career out of this topic actually, very fast. Maybe I'll do something on off-axis illumination, source mask optimization. Do a stream at that sometime. Really interesting. Okay, so you might not know this, but EUV, unlike prior generations, is a photon-limited system. Where do all the photons go? So they're actually consumed almost entirely by the lens. You lose it's not an efficient system at all. So if you were to start with 100 photons on the collector getting sent in, remember it only reflects 70% of light. So you're down to 70 photons off the first facet mirror, then 50, then 34, then 24, and by the time it hits the lens or the reticle, you only have 17% of your light remaining, and you still have 6 to go. So 12, 8, 6, 4, 2.8, and then when you finally hit the wafer, you're down to 2%. That means 98% of this expensive light you generated is just gone, consumed by the lens. This is now like the prior gen were almost like 100% efficient. Now you're down to 2%. It's this is a big problem, big challenge for EUV. So when you think about how the photons on the wafer in the photoresist, that organic film that you're trying to image the pattern, with the prior gen, you had very dense photons that would be like in the space area here that could be used to define the image, like the pixels of your image. So you're able to create like nice straight edges and things like that in your pattern. With EUV, you have an order of magnitude lower. It's actually about 8%, in relation to this. You're printing smaller patterns, but you have less photons or less pixels to create that image. What this leads is to a lot of patterning defects. So you could have a micro bridge here that would create an open if this was a metal pattern here. You could have a line pinching, which would create a short. Or if it's a via interconnect, some might be missing, some might be shorting against each other. Now, how would you mitigate this? It means you just have to dwell longer, right? So I have to slow the system down and expose over a longer period of time to get more photons into that image. This was never a problem before. It's like speed and dwell time and things like that were never a problem with prior generation. They are important for EUV. Why? It's related to the productivity of the tool. So I have here, this is just from ASML. They're quoting 70 wafers per hour at a dose of 20 millijoules per centimeter squared. So yeah, I mean this is a measure of dose. I won't go into it super detail, but remember that number, 20 millijoules per centimeter squared. You get 170 wafers per hour to tool. Again, these are very expensive tools. They're about 150 million euros each. So what if you weren't getting 170? Say you only got half of that. That means you need another tool. It's 150 million euro. That's a big problem. It's just a money problem, right? I have here a plot I pulled of the dose along this axis, and what's the critical dimension or geometry size along this axis, and then it has the years like different nodes released. So the 7 nanometer logic node came out in 2018. It's printing a particular device geometry here. But right off the bat, look, here's 20 millijoule here. That's what, the quoted throughput dose is. But even at the introduction node, that was like, almost 40 millijoule was where you needed to operate. So Now it gets where, as it turns out, as you scale the geometry down, the dose requirements go up. So this is a big problem here in that you need more tools if the dose requirement's higher, you're going to need more tools, a lot more tools. Say you had a fleet of 10 and you had half the throughput at the next node. That means you need 10 more tools. That's $1.5 billion. Not a cheap price tag. So the exposure capacity for EUVs obviously going to be a growing issue in the industry. I'm not going to talk about this because again, there's kind of a little contribution article I'm working on, I'm contributing on, where we dive into this. So stay tuned. We'll have some more. We'll have a deeper dive in this in an article form, and maybe I'll do a live space go through.